Yep. Yeah, no, that's fine, because that one's not working. Maybe after that, then I'll talk a little bit about the, and then I'll talk a little bit about the chart, maybe on chart. And so, I'm interested in how we convert aircraft such that we can, aircraft or other vehicles, such that we can accommodate passengers in a way that optimizes passenger time. And there is a wealth of literature out there about air traffic management, particularly in events, but the literature hasn't focused on passengers in this way. Right? So I'm really interested in how can we keep passengers moving through the system in the event. Right? So the way I did this is I designed a heuristic to kind of step through all of the flights in the airport and take a look at what might happen if we choose each airport to work flight. So what this algorithm does is that it takes the flights that are en route, it takes the diversion airport. And the first, sort of most important thing it does is it does a planning. Can we physically divert these aircraft to these airports? And one of the biggest reasons why you might not be able to do this is fuel on board. Not stop the aircraft in place and fuel it. It's stuck with the fuel that it has on board, and that is a major constraint. I wanted to take a second on this constraint because how we fuel aircraft is a very active area of my research. I think the research gap, sort of segueing into referring to the very end of my talk, I think a major research gap that we have is understanding the relationship between how we fuel aircraft and how we plan for unpredictability and understanding the cost that comes with overfueling. The heavier you are, the more fuel you burn, right? And so we have this sort of balance between creating more emissions and more cost, but being able to buy options if there is an event. I think that trade-off is really interesting. I'd be really interested to hear, particularly for those of you into shipping and logistics, similar trade-off issues. I have a very strong relationship with Delta Airlines. I have about 14 months of data that's flight by flight about all of their fuel consumption, how they load fuel, how they burn fuel. And I have a few studies coming out that look at the cost of carrying that additional fuel, what might be a reasonable buffer. But I think it's really interesting to think about how you could burn more fuel and be more resilient. I just think that's kind of a step. So anyway, that's just an aside. That's sort of one of the constraints there in looking at the set of flights and the set of diversion airports. Once I define the number of flights that are en route that can be reasonably accommodated at diversion airport B, I jump into estimating the time that each passenger is going to have to spend trying to get the next outbound flight. Right? So basically, I take a look at, for each flight, the distribution of true destinations. Right? I mean, 85% of people going to Atlanta Airport are not going to Atlanta. Like, where are these people on these aircraft going? Right? So I diagram this all out, and then take a look at the outbound flight. Say, how many seats can be available on these flights? How can we accommodate these people on these aircraft? Right? And so have the algorithm that runs that in general is doing that and calculating passenger wait time. Bring that back into a wait time cost, which then I add to a cost of flights that could not be accommodated. If you cannot make it to the diversion airport, you have to go somewhere. And I just assume that they're going to be diverted to some typical diversion airport. Maybe for Philadelphia, maybe Allentown, something like that, right? And so then I calculate a ground cost. I'd like to make a little bit, I'd like to make a note that the data that is driving this, the data that is driving this algorithm is from massive public aviation data that is maintained by the FAA and the BTS, data on origins and destinations, data on delays and operations, right? There's just a wealth of aviation data out there. And so I've assembled all this data, I made all of these databases such that I can know where people are really going on each flight, things like that. So we've done quite a few case studies. We did a case study of SFO, we did a case study of Dallas, we did a case study of Atlanta, and basically we just sort of take these airports offline at a particular time, and we run an algorithm and see where we might divert flights. Burbank, which is south of San Francisco, emerges as, which is way south of San Francisco, emerges as the best diversion airport for San Francisco. LA can't accommodate more flights because they already have their schedule. It's packed, right? And so Burbank has that extra capacity, but they have some flights that are coming up that they can accommodate people. For Dallas, it was Dallas Love. It's a very nearby airport, very well served by Southwest Airlines, and that emerged as the optimal airport. So as a conclusion, I come out of a case study. I like to think of it as a new use for old airports. There are many airports out there with some level of flights, so maybe they have a little bit of overcapacity. We did just go through a major expansion period for airports, and then the airlines merged and reduced flights, right? So maybe we could take these airports could actually be part of a resilience plan. Maybe that should be the way that we're looking at it. I'm going to very briefly talk about this short to medium-term aircraft hubbing algorithm. So what I'm looking here is a logistics system that has farm trade areas, freight coming into seaport hubs, and then going to the inland distribution center. And the idea that we had was to design a system with seaport hubs and inland distribution centers, and then take a seaport out and reassign the demand and supply nodes. And we do this in two ways. One is that when we take out a hub, we can assign the demand and supply nodes only to one seaport. The other, which we just call multiple allocations, that we can assign them to either. So if familiar with spatial modeling, what underlies this is the idea of hub location modeling. You have an optimal allocation of hubs given demand and supply. And so we design a sort of static flow network, and then we just take out a hub. And we collect a lot of data from BTS, and we get the optimal scenario for each airport. And so we did this many times. But to me, some of the things that come out of this that are of particular interest, that I think this gives us a new way to value the criticality of hubs. For example, we found that under many different scenarios with the variables, I didn't get into, Boston is the most costly to take out. And that's sort of a new way to think about how critical each seaport is. Right? It sort of adds a new level to the metric. Another thing that came out of it was how many backup hubs or ad hoc hubs should we establish for each hub outage or seaport outage. And what we found is that if you have two backup hubs, you can save a lot of money compared to having one backup hub. If you have 3, 4, 5, 6, it really diminishes greatly. So, for simplicity, maybe a strategy of having 2 backup hubs for every hub outage is the strategy. As my final notes, I just want to talk really briefly about what I think are some critical areas of research going ahead. I mentioned the third one is trade-off between carrying fuel on board, buying options, and burning additional fuel. I think that this is an understudied and really critical area of work. I'll go back to the top. One is thinking about day-to-day vulnerabilities of airports and seaports. We can estimate in a very static way how vulnerable each of these infrastructure is. But on a day-to-day basis, their operations are changing, the weather is changing, the operations of the surrounding airports are changing. So could we design systems and algorithms that say, where am I today? If I have a partial outage at noon, what should I do? If I have a full outage at 4, what should I do? Right? So can we have these sort of dynamic understanding of our infrastructure vulnerability? And the last one is to get collaborative decision making for these sort of algorithms, these ad hoc algorithms. The major thing I have not said is that the airlines cannot do this now. I know less about the institutional issues of the shipping industry, but the airlines certainly cannot do this right now. And I doubt they would want to. Thinking about how do we design our institutions, but also how do we design algorithms for collaboration that can showcase the benefits of doing so. Right? Currently, we have a system of collaborative decision making. When the capacity of an airport goes down, the FAA has the system where the airlines are allowed to work together in the short term to make that capacity the most efficient. Well, maybe we can think about collaborative decision making in a broader way. When an airport goes out, can the airlines get together, work together to start accommodating each other? So thank you very much for having me. I really look forward to this discussion. Right now, we let anyone be converted on any carrier, so we're doing full collaboration. The other thing I should have noted is that in the aviation algorithm in the immediate aftermath, if a flight hasn't taken off and the outage occurs, that flight doesn't take off. So if you're only servicing a small number of flights, there certainly would be, especially at an airport like Burbank, there certainly would be staffing issues. So I think of that as adding on another level of constraint. Right now, we just have blocks. Right? So for each 15 minutes, we have a certain number of slots, certain number of take-ins. They already have operation, and then we fit them in. To me, that would be a next level of constraint. Do you have gate staffing? Right? And maybe that's part of this day-to-day vulnerability. If San Francisco is particularly vulnerable, they alert Burbank and do some staffing up. Your question also touches on, so when we're planning work about airports, many airports have so much money they don't know what to do with it. And they're not allowed to take it off the airport, but they have so much money. They really don't know what to do with it because they're not allowed to take it off the airport. And so the idea that an airport like San Francisco likely has the money to support some sort of uptick in staffing if there was a bad day. Yeah. My explanation for that is that in the heuristic algorithm for the immediate aftermath of an outage, we were very careful to incorporate capacity because you can't pick JFK as your backup airport. Right? JFK is at capacity almost all day, right? So we were very careful to include capacity, and the way that the algorithm is designed, it really allows for that. Right? It's sort of stepping through the process, and it's not a linear program. We have not incorporated capacity yet into the shipping model. It's very, it's sort of at its first stage, and our results are very colored by that. Because I think if we add in capacity constraints at seaports, the number will be more than 2. But so, it's not, the model isn't fully formed. To me, these are the things that, when we incorporate these critical outputs, we will be able to. Envisioning here is not a flight having to divert. I'm sure we've all circled above a hub airport because they have weather or something like that. You divert somewhere where you don't want to be. They wait it out for 2 hours and then you go on to the hub. That's not the kind of outage that I'm thinking of. I'm thinking of like an earthquake or sea level rise or something that compromises the infrastructure so that you are not landing at that airport. Right? And there's no hope, because if it were a system where there was a hope to land, the airlines would never do this. They would want to go and hold and wait and hope that they could land where they're going, and then they get to, they call Bengal Field, which is we have to land now, and then they go to their diversion airport. That would be their preferred. But if you know you're absolutely not going to land at the airport, en route you can divert and have enough fuel to make it to that airport. So it's a very specific scenario.
Hi everyone. Thank you for the invitation again, Brian. So I'm Claudia. I'm a junior faculty in the Department of Civil and Environmental Engineering at MIT. And what I want to do is talk, first of all, tell you a little bit about what my research group does and focus on one topic, and mainly go through several case studies with different cities that we've been working with. I won't go into the technicalities too much, just maybe give you some flavor of what's behind it, but not really focus too much on it. So a lot of our research developing tools to come up with more intuition about how individual vehicle performance or traveler behavior actually impacts large-scale network performance. So here in this graph, it might not be very visible. The x-axis is detail. The y-axis is how tractable or optimization-friendly the models are. So I've plotted here through the three traditional families of traffic models, macroscopic, microscopic, and mesoscopic. And so typically, macroscopic models are less detailed, very tractable, and typically used to solve very large-scale optimization problems and to model large areas. On the other hand, we have, on the other extreme, microscopic models, which is mainly what I'll focus on today, which are very detailed. So they try to describe, for example, the fact that we have, as travelers, very heterogeneous behavior, the fact that we have different vehicles that have different performances, different technologies embedded in the vehicles. So they're much more detailed, more high resolution, but that comes at the cost of not being able to use them as efficiently to solve very large-scale problems. So first, even just the complexity of developing a large-scale model, then let alone the complexity of using it to actually solve problems at the scale of city or region. So one research, with the research lab group, looks at those two extremes and says, first of all, can we develop macro models, macroscopic models, that are more detailed in accounting for uncertainties in supply and demand, and can we use those for large-scale optimization? And then the second area, which is what I'll focus on today, can we take the already existing high-resolution microscopic simulators and develop algorithms that allow us to solve very large-scale problems with them? So this is a snapshot of microscopic simulators that I've used a lot. I used to live in Switzerland, and they had a very sophisticated microscopic model of the entire city. So on the upper left, you see the full city network. As you zoom in, you see something that might look like links. You zoom in even further, you actually identify links that are gray, intersections that are yellow, and then you actually see the individual vehicles that are here depicted in blue, and then in this intersection, you can see the traffic lights in red and green. So basically, this snapshot is to show you that to develop these models, we need a lot of data. Data on the supply side, what are the traffic management strategies that are prevailing for a given time of day? How do we interact? How do we respond to traffic? But also a lot of data in terms of traveler behavior. Where are individuals going? How are they reacting in real time to traffic, to congestion? These are very sophisticated tools, and what the issue in terms of their use in practice is that it's very limited in what types of problems we can use to solve them. Mainly because there aren't really practical algorithms to embed these really sophisticated tools to solve either traffic management or network design problems. So what we focus on, what our work focuses on, is how do we design practical algorithms? And by practical, what we mean is, can we limit the number of times we have to call these really complicated simulators and still come up with good solutions to a traffic management problem or a network design problem? Okay? So the way we do this, and I'll skip over all of the math, but the way we do this is basically combine information from these very sophisticated simulators with information from much less sophisticated macroscopic models. So we think these macroscopic models aren't as detailed in their implementation to manage supply, but they do have great advantages mathematically in terms of their ability to perform large-scale optimization. So what we do is combine ideas from both models to try to come up with a good trade-off between using a very sophisticated model but performing very large-scale optimization. So I'll show you a few case studies of this. So this is called simulation-based optimization, embedding these sophisticated simulators within optimization algorithms. This is again the city of Lausanne, a map. On the left-hand side, the corresponding network model that we have and a snapshot. And I'll show you some case studies that focus mainly on signal control. So we looked at, if you look at one of these maps, there's a few dots, black dots or circles around the city. We identified 17 intersections distributed across the entire city, and we said, can we retime the signal plan at these 17 intersections to try to reduce or improve travel time throughout the entire area? So this is challenging mainly because you need to be able to predict. If I were to retime an intersection here, I need to be able to predict how individual travelers are going to react to that, how they're going to reroute, and hence how that's going to impact congestion in other areas of the network. Okay? And so this is one of the largest scale case studies that we looked at. So the network is about 600 links, 200 intersections, where we're controlling only 17. And we looked at even in peak barrier demand. So we're simulating about the order of 12,000 trips. And so the key question was, can we come up with a better solution than what exists currently in practice if we only run the simulator a very small number of times, and in this case, the small number is 150. So we're solving problems that are of dimension of 100, 200, and we're saying we only want to run the simulator 150 why do we do this? Because that's typically the way agencies are using these simulators. They're really limiting in a significant way how many times we're running them. So our question is, if we were to put ourselves in that context, could we do something that is better? These plots show every link is colored according to average minimum travel time. So this is a before and after situation. Before on the left, higher travel times are in red, lower travel times are in green. So basically we showed that you could actually come up very quickly with signal plans that are better at city scale by using these algorithms. This led to a collaboration with New York City DOT. They're also developing very sophisticated models of areas of Manhattan. And we looked in the area of Queensboro Bridge, limited here by the oval. And so this area is a set of links that connects the Queensboro Bridge that connects Queens to Manhattan, and looking mainly at morning peak periods. So this was a really complicated case study for several reasons. The network is very congested already, so any local, even small change that you make can have not just significant impacts, around a specific intersection, but that can quickly propagate and affect links that access or egress to the bridge, and that will have significant impacts. That's the most actually heavily congested bridge among the bridges that connect Manhattan. The other thing that made this very complicated is you have this grid topology, which in terms of actual travel behavior has many complex decisions. So your actual route options, if something goes bad at one intersection, there's a significant number of potential alternative routes that you could be reconsidering. So it makes it more complicated to actually predict how travelers are going to react to changes in the way you're operating the system. And then we have, of course, multimodal traffic in the area, buses. There's very heavy pedestrian traffic at the intersection, so there's actually not much, a significant part of, let's say, the cycle time at the intersection is devoted to all red or red in a given direction to favor or facilitate pedestrian crossing. And then the last thing that made it complicated was this grid topology with very short links. So that means that links are actually likely to spill back, which means that you're going to very quickly have spatial propagation of congestion. So one of the things we've been working with them is, in this very complex context, can we think differently about the way we're operating the signal? And in particular, is there a way to operate the signal such that we limit the spatial propagation of congestion? And we're thinking in particular of how that affects the access to the bridge, but more generally, if we can confine the spatial propagation of congestion, we might be better off also in terms of general travel time or throughput, and in particular, reduce the number of people that are affected by that congestion. So we looked at retiming their fixed time plans in this area. This is the thing that we're just shifted a bit. And so this shows, for example, compared to the prevailing signal plan, we compare the plan proposed by the algorithm, again, running it for, I think, 100 times, a very limited number of simulation runs. And we color the links here according to the ratio of travel times under the proposed new plan and the existing plan. And so the links are colored on light green if there's more than a 20% improvement in average length travel time, dark green if there's a 20%, orange if there's a decrease of up to 20%, and red if there's a decrease of more than 20%. So overall, even though the algorithm is designed to actually improve the spatial propagation of congestion by reducing queue length, you actually observe a significant improvement in travel time. This also led, I don't think I have figures on that, but we also saw significant, very significant improvements in the occurrence of spillbacks in throughput as well. So this has led us in an ongoing study with them, thinking more and more about how do we confine the spatial propagation of congestion, and to what extent can that be done through simple signal time. This is a snapshot that looks at the same thing, the ratios of performance from the proposed plan to the existing plan, but this is now looking at average link queue length. And one of the things that this has led to, a new topic of investigation with them, is there's typically in New York priority given to progression along the avenues, and so the streets are actually secondary. So one of the things we're looking into in larger case studies is to what extent can we make a more balanced allocation of capacity, not giving such high priority to the avenues? What impact would that have in the through traffic in Manhattan? So this was an initial study that we did with them looking at fixed time plans. Really great results. Again, this is all simulation-based. It has not been deployed. And this led us to actually, for that same Queensboro Bridge area, to develop algorithms that are traffic response. So what they do basically is we develop offline a set of fixed time plans, and what we do in real time is simply select from them. So we propose a few different metrics like appropriate plans to reduce, again, the spatial propagation of congestion. try to analyze a larger network. This is now about 900 links. This is in Midtown Manhattan on the western part. And again, here what we're going to be doing is investigating whether we can balance off the priorities and not give as much priority to traffic along the avenues that rather focus on the through space. One of the things that is really neat about these simulators is that they actually represent individual vehicles. So they are suitable tools if you want to kind of look into how vehicle technology might affect congestion metrics, and in particular how fuel consumption or energy consumption is affected by traffic management. So one of the things we did is we coupled these microscopic simulators with microscopic fuel consumption models. So what that means is every 3 seconds we get from all these 12,000 travelers instantaneous speeds and acceleration. We plug that into a microscopic fuel consumption model or energy consumption model that gives us instantaneous fuel consumption and energy consumption. And then we plug this into the algorithm to say, can you come up with traffic management strategies that improve traditional metrics like travel car throughput, but also improve energy consumption and emissions? So we come up with algorithms that do this. This is a snapshot of the sub-area within Lausanne, a before and after analysis of average fuel consumption per link. And so what we could show is that we can actually come up with algorithms that indeed reduce fuel consumption at a network level, but not at the cost of actually, so still with reductions in travel time and throughput. So these are not necessarily conflicting goals. We extended the results to look at into emissions, coupling the traffic simulators with microscopic emission models, and had also similar insights in terms of there's not a trade-off to be paid. We could tie our traffic lights in a way that they are beneficial for emissions and still beneficial for our traditional metrics that agencies are typically looking at. One thing I wanted to mention, so Brian asked us to identify a few areas of future research. One of the things that I've been working a lot that I'm really interested in is how can we use all this new data that's available to think differently about how we measure performance in the network, with a big focus on measuring reliability, measuring robustness in the network, and then eventually operating the systems so we actually guide them towards more reliable and more robust operations. We've designed algorithms that try to improve travel time variability. That is something that is of high value to travelers. And we've also been looking into how that couples in with transit systems. So can we design algorithms that if you're looking into multimodal trips, you know, you do a car for a first leg and then potentially moving to the transit, how can we design algorithms that improve, for example, the transit operations to reduce travel time variability? So just 2 more comments, and then I also want to go back to Brian's question about what are future challenges that I see. We've been working, one of the things I'm really interested in is how, if you have a city with an existing set of urban mobility services, how can you design on top of that real-time, on-demand mobility services that complement what we already exist? And the case study we've been looking into is how do we complement in Boston the transit system with new car sharing and bike sharing services. So that's a work with Ford and Zipcar, and really looking at it not just from the perspective of, you know, Zipcar or the individual company that's interested in deploying this on-demand mobility service, but really looking at it from the city's perspective. What are the links in the transit system, for example, that we could be complementing and that could make the transit system more interesting if those services could be overcome or traveled to other types of transportation services. And we've also been developing something that's mathematically more challenging, I think, which is algorithms for calibration. So these simulators, they can be very detailed, but there's also plenty of data and plenty of models that need to be estimated. And so we're really lacking in this field algorithms that can make, let's say, do a better job in calibrating the models that we actually trust them more and we actually think that they represent or replicate current supply and demand conditions better. And so in terms of what areas I see for real challenges, I think one of them is how can we develop tools that allow agencies or potential companies that want to develop urban mobility services to get a better intuition of how the spatial distribution of demand actually impacts congestion. So typically what we know is, you know, there's a bottleneck at this area at this point in time. What we don't know is what is really causing that area, that bottleneck, sorry. And so if we had some tools that give us more intuition about how the spatial temporal distribution of demand, where people are starting their trips at what time, how that actually links to congestion, I think we could come up with mobility services that trigger the causes of congestion, not just the consequences, which are these different bottlenecks. The second thing that I think is really interesting but also challenging is, again, how do we take all this very detailed data that we're collecting at the scale of vehicles and travelers and actually use that to forecast what can happen at a very large scale? This is, of course, forecast how their new traffic management strategies that are going to become more and more connected and responsive, how those should be redesigned to account for potential congestion that is going to propagate soon. And finally, a lot of what we're doing recently is looking at how connected mobility and autonomous mobility is going to be impacting or potentially impacting the way we operate our network. Should we be thinking about the way we operate them differently in that context or not? So those are a few of the ideas of things that I think are really challenging and that I think we need more work and focus. Thank you. So usually the agencies come with their models that are calibrated. In some cases, the map I showed you here is a calibration study with a metropolitan area, and there the problem is we can redesign algorithms to calibrate them. But our algorithms, other than this calibration algorithm, are all based on existing calibrated models, and the question is how can we make better use of these models to solve different types of traffic management? Yeah. Yeah, definitely. So the snapshots I showed here, for example, this is a snapshot of Midtown Manhattan that was all been calibrated and developed by New York City DOT. This is a snapshot of the area around the Queensboro Bridge developed by the DOT. There's different types of software, of course. Yeah, it depends on the agency, what type of software they use. Yeah, many different types. So this one specifically was based on those ones that we do with MapSim. We're doing now new case studies with IMA and MinSim. So it's software independent. It really depends on what. And I think a lot of the choices of what software to use is also application specific, depending on what are the key factors of demand that you really want to account for, and which software represents that. Yeah. So far, a lot of our cases have been recurring peak period traffic. So I think that a lot of the data that we're now collecting is giving us a much better understanding of how people really behave, and in particular how they behave in real time. So how they respond to changes in congestion or to advice or guidance from the agency. I think there's still a lot of work to be done there. And I think one of the complexities and one of the things we've been working on in these calibration algorithms is how can we get that typical understanding, which is, and these models are typically based or formulated and estimated and validated based on major cities, typically in the U.S. and in Europe. And then when one specific city wants to, for example, New York wants to actually model their traffic, well, there's attributes or factors that have not been taken into account. So, for example, in New York, one of the things is how familiar the users are with the way the system is being operated and how we want to allocate the system. That's something that these models typically don't account for. So one of the things we're really working on is how do you design algorithms that once you actually want to tweak and fine-tune these models to specific considerations of your network, that you can still do that. Because currently we really don't have ways to do that. So. Mhm. Yeah. 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 Exactly. And I think for what we've done so far in autonomous mobility, one of the very interesting questions is, let's say we had an understanding of how the autonomous vehicles are potentially really going to interact with infrastructure and with other vehicles, which we really don't have at least a lot of consensus on. Let's assume we have that. How are people that are non-autonomous vehicles going to behave? And based on recent, let's say from millions of what Google has reported, it seems like that's going to be a major factor in terms of how individuals that are non-autonomous vehicles might change their behavior to actually outgain or react or respond to autonomous and more connected vehicles. And that's something that I think the role of these tools in that case is even more hypothetical in terms of we can test out scenarios, but there's definitely a lot of major questions about how the technologies are going to work and how people are going to respond. And we don't have the data for that. Yeah. Yeah. Mm-hmm. Okay. Okay. So the state of let's say 99% of the algorithms that exist that you could use to solve these problems are typically general purpose algorithms, meaning you can use them to solve any type of simulation-based optimization problem. It doesn't even have to be trans. So that's good. The disadvantage, and they're designed to achieve mathematically really nice properties of asymptotic rates of convergence. And that's all very great to publish, but in terms of how they're being used in practice, none of the criteria are being satisfied to achieve actually these properties. So in terms of practice, the way they're really being used is saying, I have this amount of time to actually solve my problem or this amount of resources. I'm going to solve my algorithm at this same time and assume that the best solution found so far is the one I'm going to use. So now we reverse engineered that and said, okay, now since we know that's the way they're being used, can we come up with an algorithm that within that amount of time give you a good solution? There's no guarantee that this is some optimal solution according to whatever definition of optimality, but it's something that should lead to a significant improvement compared to surveillance strategies or the initial point, or whatever you currently consider to be the best solution. So there's no guarantee that that's the optimal solution, but that's something that, based on my work with agencies, is not a big price to pay. They're less interested in what the optimal solution is versus something that makes more practical sense and accounts for, let's say, the real issues under which the algorithm would be used.
Okay, so we're going to now take a break, and we'll start again hopefully at 3:45. So for about 20 minutes, please do take advantage of time to look at the posters. We're obviously take a break as well. Our short speakers will be happy to talk more about what they have presented. So see you in 20 minutes.
of work that we're doing. The first thing is that as we get more and more information, geospatial information on how cities are laid out and how we have patterns of impervious and non-impervious and transportation and infrastructure in cities, you know, we go very much from a bare bones, like these are the watersheds around Knoxville, down to, you know, we start seeing differences in land use. And so you can see downtown here, we have this very compact, like urban core. The red is basically, you know, the most dense development that we have in a city, right? And so it starts kind of telling us a tale about that city and what that city looks like in terms of land use, right? But in stormwater, we have this other kind of complexity that we deal with, which is connectivity of urban areas, right? So not all impervious areas are really the same in terms of degradation. So this is one example of basically, if we take the runoff from this building, it dumps straight onto the parking lot in front of the building. It goes right into a stormwater sewer to the stream, right? Very fast process. And that would be connected impervious area. Everything hits really quickly when it rains, and we get a flush of water out of our system. The other would be disconnected, where the rooftop runoff from this building goes onto a green space. It's allowed some time to infiltrate, and so there's a little bit more natural process involved with that. It doesn't have the same impact as connected impervious area, right? And so we understand this, but it's very hard to when you look at a map, figure out what those spaces are that are connected or disconnected. And so some of the work we're doing right now is related to this imperviousness and impervious connectivity. So total impervious area actually doesn't predict stream or ecological degradation, as well as things like connected impervious area, right? And so we know that in literature, but there's a gap as to how to calculate or how to understand that. So effective impervious basically means during a given rain event, how much area of my watershed is contributing, right? Different size storm events, we may not even get any runoff from a green space where we get complete runoff from an urban area, right? So very different dynamics depending on what size event we have. And then directly connected is what I was just talking about. So the issue that we have here is that current estimates of how to figure this out, this connected area, are basically we take a bunch of rainfall runoff curves like this, and we take our smallest runoff or smallest rainfall events and we fit a curve to that, and we know that only during small events, the only kind of portion of the watershed that gets activated is this connected impervious area, right? Okay, so we can get an estimate using that. The issue here is that spatially, in terms of our watershed, we have no idea where this is occurring, right? So we get a number, but it doesn't really tell us where that's happening and where that connectivity is present. So I've got a student right now who's working on this issue a little bit. He's taking this high-resolution LiDAR data and breaking it up into parcels and essentially assigning impervious and basically impervious, non-impervious to each of those. And at the same time, burning in our hydraulic features. So taking the stream channel, taking our pipe network, and basically expanding what we call this hydro network into the watershed, right? And then at any given point in our watershed, we can calculate what's the distance from that point to the closest piece of the hydro network, and then what percentage of that travel pathway is impervious. And what that gives us is what I call these impervious heat maps. So the importance here is what we can start seeing is what parts of the watershed, so this is kind of our creek and a connection right here inside of Knoxville, and the red areas kind of show us where these areas of highest connectivity are, right? And so in terms of transportation, obviously when we're in an urban core, we have really high connectivity of our stormwater areas, right? And when we're in kind of a dense constructed area, we have really high connectivity. So if we're looking for a place inside of a watershed to get the biggest kind of ecological benefit for our work, we got to have to target these areas that are most connected. Right? And in urban areas and in downtown areas for transportation corridors, it can be really hard to find a space. And so a lot of places are looking at these mitigation strategies where, I can't do anything in this particular location due to my space constraints. I can't really fit a practice in there, right? So I'm going to pay money into a bank. I'm going to do a practice somewhere else. Where if you're going to do that, what kind of areas should you be targeting, basically, with the money you're collecting under that effort? Right? So this is these are the first steps towards kind of understanding for us, how these watersheds are really connected and what kind of difference that makes in terms of ecology and getting the most benefit out of the practices that we have. Right? So in terms of volume and where the water's coming from, that's kind of where we're at. The other thing that we have in terms of stormwater is obviously this difference in hydrology, right? So if we were to take, this is just some simulated results from, let's say a 5% impervious watershed. I bump that up to 36%. I get this huge peak of stormwater. I get way more volume. And so a lot of our green practices are they're not just trying to deal with peak runoff, they're trying to deal with this issue of volume. Okay, so this is a very old schematic, and I've been yelled at it many times, that 40% evapotranspiration is very low. If you're to go into, into the Appalachians inside of a natural watershed, you're going to get more like 80% of the rainfall in a given year goes into ET. But what it does for us is it paints this picture of what happens when we increase impervious areas in our watershed. And so we're trying to deal with that. And so we've kind of got these three things we're trying to work with inside of our water quality component, and that's our peak flow control, our water quality. I always point out this flipped over crab right there. I always figure a crab's like a tough animal. And I'm like, if you did that to a crab, there's got to be some water quality issues there. It's a sad thing to see a crab get destroyed. And then the other thing is volume control. So as we take our primary, our upper watershed streams, and we start having this imperviousness, we start lowering our groundwater tables and affecting base flow inside of streams. And so volume control is something that is kind of at its infancy in terms of regulations, but in Tennessee, this is about to go into effect that basically we're going to have an inch of volume control on our development, which means you're not treating and discharging an inch. You cannot have the first inch of rainfall leave your site, right? And so in terms of, and that was a rule that EPA was proposing and then kind of pulled back on, and then we'll see where it goes from there. But in terms of a highway corridor, what do you do now if you're building new infrastructure and now you have to somehow hold, that first inch of rainfall on your site? So green infrastructure is kind of of what we've started to use to deal with this issue of volume, right? So all these different practices essentially come down to something like this. So this is just a bioretention area split in half. And really what we're trying to get is evapotranspiration, and we're trying to get exfiltration, right? Those are like the two primary hydrologic pathways we're trying to promote to keep water out of our, or to kind of allow water to perk to our waterways slowly. So the challenges that we have in terms of a transportation corridor, we have very linear systems, right? You can't go out there and build a 2-acre wetland or a big ground bioretention out there in all cases. Infiltration versus geotechnical needs, right? So the water people, we're trying to promote infiltration. I'm saying don't compact everything like crazy because I want to infiltrate. Vegetation selection. So in highway corridors, you have to be very careful with what vegetation you're selecting. You know, it can't be too high. It can't be a hazard in terms if there's an accident. Steep degraded outfalls, and then urban areas are obviously an issue. Advantages is that in some cases we have pretty high green space to impervious ratio. We have big, nice filter strips and swales. We have relatively flat slopes in some cases. So all those things are kind of in our favor. So I'm going to highlight a little bit of research from NC State and some highway work that they've done recently. And basically they studied a bunch of these filter strips and drainage swales along highway corridors. And they had a very nice setup where they were collecting basically water coming off of the interstate. And they were able to sample that. They were able to sample water after it had come down the filter strip a little bit. And then also able to sample water in the swale, right? So they're kind of capturing water at all different points to see what happens to it. And the most interesting thing is down here in terms of this volume reduction, right? You're letting water flow down this nice grassy filter strip, and you're getting really limited infiltration rate, right? And so this goes back to the question of infiltration versus stability of our side slopes, right? And what they did, they went out there and they started doing some compaction tests, and basically what they found is that this lower infiltration rate was basically associated with lower amounts of compaction, right? And so we know that in terms of soils, we are, I'm going to move this over here to get it out of the way. I think I caused an issue. There we go. Once you get that feedback, it's hard to get rid of. So basically, the more compaction we have, the lower the infiltration rates. So I think this is kind of a big question for transportation corridors going forward is, you know, can you optimize that compaction versus allowing infiltration, right? And we've got kind of people on both sides, and each want different things. The other thing that we're doing some study on is a project that started up in up here around Baltimore and DC has been one of the pioneers of using these. These are these stormwater conveyances. The idea is when you have outfalls from transportation and other outfalls, a lot of times the stream has dropped over time, right? And so you get these huge drop-offs from your outfall, causing these giant just swales of erosion that occur. And so these regenerative stormwater conveyances are something that's started to be used. It's basically a mix between a filtration bioretention area and a stream restoration. And so you put these big boulders in here to hold grade, and then you also allow infiltration through the center of the system. I worked at Biohabitat for 2 years, and so this was kind of something I picked up from them when I was working there. And so we're doing some work on that right now. I've got a student out in the field building one right now. This was me yesterday out in the field, getting sunburned and sweating to death. So what we want to look at is the design criteria for this is a little bit undefined, and so we're doing this Flow 3D modeling of these systems, and basically we've got these models built. We're going to collect data from the site to figure out how the flow actually runs through the system, calibrate the model, and then look at different design scenarios to see if we can optimize the system a little better. And then we're also going to look at groundwater fluxes, that if we're trying to shed water into the groundwater table, you know, what's the effect on the local groundwater table, and how is that influenced by our infiltration? So that's another big question in stormwater moving forward, is we all are just trying to pump water into the ground, pump it into the ground, pump it into the ground, and we have a tendency in the environmental community of just passing our issue to some other group. So air passes to water, passes to soil. So that's an issue is what are we doing to our groundwater tables, and what's the overall effect on our structure. The last thing I was going to talk about is just some modeling we've done to start looking at climate change impacts on these systems. It's a really basic study, but in general, if we've got this practice, in this case a bioretention area, and we put these climate scenarios through it, what's the effect on its functionality? So obviously we've got more extreme weather that's coming, and it ranges. It's different based on different areas. This will be a scenario under present scenario, what we would call extreme weather, future scenarios, and then this is kind of the difference. And so, it depends on where you are and what the impact is. I was working with somebody in Cleveland, and they were like, it doesn't look like my system really functions that much different. And I'm like, maybe it does. So this goes into resiliency in our systems and our infrastructure, and how can green infrastructure build resiliency, right? We've got stormwater pipes all over the country that are reaching their design life, or now they're carrying more water than they were intended to carry. And so can we build in green infrastructure to buffer that capacity to some degree? So we use these bioretention models. I can skip through this stuff, but essentially we have these calibrated models that we run for bioretention areas. And we use this downscale climate data. I work with a guy in my department that does climate modeling, and basically to see how the system functions differently. And so we look at our runoff basically under our base scenario, which was 2001 and 2004, and then how is that going to function under future scenarios. So what this shows us is how our water gets partitioned from runoff to drainage. And basically, if you look at percentage of rainfall going through a certain area, it doesn't change. If you look at the overall percent difference, we get way more overflow under climate change scenarios. So we get more intense events. They cause more overflow out of our systems. All right, so basically these are highly, I thought I had one. Oh, here we go. Yeah. So for climate projections, and this is a very important part of water, obviously precipitation drives the whole system. Spatial resolution of data is huge. We're going from global climate models where, let's say the state of North Carolina would be 2 cells. We'd have 2 data points for the entire state. And now we're downscaling that so we can start seeing at a city scale what the difference is. But temporal resolution is a huge issue, right? In urban systems where we have really fast things happening, we can't really use daily rainfall projections to tell anything about the system. Yeah, that's great. All right. Okay. Questions?
So one thing you said was the connected impervious surfaces, and there are certain hot spots, and if you want to do the best thing to block something in certain locations.
Mm-hmm.
I wonder what your thoughts are on how far we are from that being a practice that's actually used. Is it something that you're seeing used in the city, or you mentioned like banking and maybe one different way of doing it, make that money.
Mm-hmm.
It seems like a really great idea, but I'm wondering how far we are using it.
I think that, the banking is definitely occurring, but there's no real mechanism for where to put that money after you collect it. I think there's maybe a couple of studies looking at this right now. Like University of Minnesota is looking at it. My student's looking at it. But there's not a whole lot of work into it. But I think the idea is that as we get more data, we're able to do these things a lot better. And so the issue with our work, and I'll tell, here's the caveat, this is straight, if I want to improve ecology inside of a stream, where do I put it, right? And so after you kind of prove that concept, then you have to look at, okay, is there space there? How much is it going to cost? Because you're basically saying, I'm going to put it in this dense area. That's the most expensive land cost also. So I think from an ecological standpoint, that's where we're trying to go, but there's a lot of other layers that have to go onto it. We're taking this data and we're trying to basically calibrate this model using a bunch of rainfall runoff data that we have for the city, and basically trying to show that, yes, it does make sense that this rainfall is coming from this area. And so I think after we finish this, I'm hoping that, those things will be more of a reality.
As far as the banking process, it's like the process period. How's that going to solve the problem with the weather and something else?
I totally agree.
For connectivity, there should be a way to say, okay, we can't do it right here, where can we do it that will affect that area?
Yeah. Yeah, and so usually when they do that, they talk about like maybe sub-basin scale. So yes, you can do this, but you have to use that money in the same relative location. But yeah, I think that's important. Obviously, is using that money or trying to get that environmental benefit in the same location. But I think this kind of goes a long way toward targeting areas, because there are a lot of practices that go in an area that's not really going to benefit the system very much, because there's a lot of space. One of the issues is space, and so if you've got green space, it's a good place to put a BMP because you can put it there, but that doesn't necessarily mean it's going to really have any ecological benefit.
Question. So there's a volume issue for these low-lying coastal areas. A lot of the alternatives don't seem to be practical there.
And
what do you see as ways to deal with that issue?
yeah, so for some of those applications, it's all about available space, because about the best thing and the cheapest thing you can do is run water in a thin sheet over a large green space, and that's the best thing you can do. But it's a matter of available space. So I think the question is, when you put water into, because in the low-lying areas you have high water tables, and a lot of practices are not regulated as being usable there. But I think the question is, how do we actually affect the groundwater when we do that? And I don't know that anyone knows that really well.
Other question? Okay. Thank you very much. Okay. And our final speaker for this afternoon will be speaking on the topic of sustainable land use practices. This is Michelle Byler. She's at Bucknell University, but I also understand this is a homecoming of sorts. She's a proud graduate of the University of Delaware. So, all right. So I had to do that. These are our hosts. So Michelle, it's all yours.
Thanks so much. I'm really excited to be here, especially to talk about this topic, sustainable land use and transportation. This is really the area of my research and my teaching. And today I'm going to talk about a little bit of background with this interrelationship between these two disciplines, because I know there's a lot of interconnections between civil engineering, urban planning, and how do they really relate. So I'm going to talk a little bit about that. Then I'm going to go into two specific projects that I've been doing while I've been up at Bucknell that kind of look deeper into the opportunity for mode shifting and using land use as a way to guide our transportation engineering decisions. And then at the end, I'm going to talk a little bit about these future research opportunities. So given that we've had four really good speakers talking about, the time to change is now and the motivation for sustainability is really important in this current time frame. I'm not going to spend too much time on this, but I think what we need to take away is this understanding that land use and transportation can guide not only how we build our infrastructure, but how people can use it. And the usage can really affect, some of these kind of more global issues. Yes, it sounds like a local change to go and put in something like a sidewalk, but ultimately if we do this kind of on a broader scale, there's an opportunity to kind of address some of these global challenges through mitigation and adaptation. So I'm going to start off with this figure here. So this might look familiar to some of you, this interconnection between transportation and land use. This is the traditional cycle that you'd see where, you think about a typical roadway, a corridor, where, you're adding more lanes to it. More people are able to use that facility and to drive further and further away from their original area, perhaps maybe for commuting. So maybe they work in an area, but then they live further away from that. So as you build those roads, people can have more accessibility and live further out, ultimately then affecting the land use, changing the type as well as the value of it, pushing that demand for suburban sprawl as we know it as, and essentially then ultimately increasing that traffic, right? Pushing more away, more people have that demand to live further away from their job. Maybe if they're commuting an hour and a half, this is not unusual, and that increased traffic, as people have that opportunity, then you have more demand. And ultimately, then your level of service decreases on these roadways, and then you continue to add more lanes or more roads. So my question is how do we break this cycle? If this is the cycle that we keep doing, what can we do from a transportation and land use standpoint to stop this? And obviously, today there's only 15 minutes to talk, but there's lots of mechanisms to do that. And we've heard some speakers today touch on these topics. I just wanted to mention a little bit about smart growth. This is kind of a new wave in the urban planning realm of trying to bring back a lot of those walkable, compact development, mixed-use land styles to kind of revert back to what we used to do before the automobile era and the emergence of lots of roadways. So smart growth is really where it's at, and I think a lot of the new urbanism strategies are really taking into effect. Building off of transit, corridor efficiency, a lot of those. But today, I'm going to spend most of my time talking about mode shifting and how land use and transportation can guide these decisions and allow and encourage people to feel confident and capable and comfortable with making those shifts. Ultimately, and this is very familiar to us, right? When we see, especially towards your more urban areas, the opportunity for people to be sitting on a roadway in congestion, and it's just an accepted thing. It's now part of our nature to feel, oh yeah, okay, well I know that I'm going to be sitting in traffic for 20 minutes on my commute home, and there ultimately I'm going to be doing a drive of an hour, and that's accepted, right? So how do we get people not to be okay with that? And also, we see, even, around areas, in urban areas, we see seas of, parking lots, right? Just lots of pavement, lots of parking. How do we, again, get the kind of common standard to go away from that and really getting people out of their cars, onto the streets, interacting with each other, having that face-to-face social interaction, and choosing some alternative modes. So one solution that is prevalent is trails. And this is really what my area of research has been within the last couple of years at Bucknell, is trying to use shared use pathways as an alternative, not as a recreational tool. Yes, it can serve as that purpose, but for commuting as well. So how can we really look at the network of shared use pathways to help us to build those land use and transportation connections? And when is it applicable and when is it not? So without going too much in depth about the benefits, you can think about the advantages of getting people out of their cars, right? There's a lot of public health and wellness advantages associated with the physical fitness, the opportunity for even children to walk to school, things like that. And that really gets involved with how well is the network connected, right? So looking at connections between not just shared use pathways, but connections between the pathways and transit nodes and other types of nodes. Also, it's really important to think about those trails as places for community identity and social interaction. And that's something that has changed over time. As we've shifted more towards the car, you could be in your car for, the entire commute, and you live in a suburban area, you drive into your driveway, close the door, you do the same thing over again every single day, and you never actually have to interact with your neighbors, right? You could be in your car and just live in that home and not see anybody. So these are things where we want to try to improve that. And one area that is really taking off is this concept of rail to trails. So essentially looking at abandoned railroad right-of-ways as opportunities to transfer that the right-of-way for shared use pathway mobility. And this is really kind of a hot topic because there are a lot of railroad right-of-ways that are not being used effectively, and essentially using it for ped bikes, you can preserve that right-of-way, that railroad bed, if in the future you want to go back to that. So the first project that I'm going to talk about just briefly, kind of at the surface level, is this concept of trail impact analysis. And this was a project where our goal was to figure out, if you put in something like a rail trail, how do you know what level it impacts that area, right? You want to know what you're putting in, and you want to understand its relationship and the effects on the land use around it, and as well as the community in putting in that infrastructure. So how's it affecting travel demand? So to do that, it was a team of 4 of us, actually 2 students and another faculty in the economics department at Bucknell and myself. We needed to come up with a very clear process for going through and figuring out how to analyze rail trails. And so we had a number of steps, but primarily we needed to really go in depth with how we were going to do this data collection. How are we going to figure out how many people are using the trail, when, why, for what purpose, and ultimately analyze this data to help us to make better decisions, not just in terms of improving that trail, but trails in and around that area as well. So we applied this method to the Buffalo Valley Rail Trail. So this is a trail that's located in Union County, Pennsylvania. So those of you that might be familiar with Bucknell, it's located in Lewisburg, Pennsylvania, and this rail trail connects Lewisburg all the way down to a town called Mifflinburg, Pennsylvania. It's about 9.2-mile trail, and if you notice, the trail right-of-way is pretty much in line, parallel with a major U.S. route corridor. So it's Route 45. This is a very well-known route that people take to go out to State College, lots of traffic, good volumes, and it parallels that route. So this was a good opportunity for us to figure out, how can we get people perhaps not to use their car for some of these shorter trips within that 9.2 miles stretch. And so it was nice because in 2011, the trail was open, and that was actually when I came to Bucknell. So right away, I threw in some automatic counters, and we started with some data collection. So we used some infrared trail counters we actually installed them at the mile markers at the locations where the yellow stars are. And since then, we've actually added a few more. These infrared trail counters are really neat devices. They look like this. They fit kind of very well inside of an electrical box, and you can just hang it on a mile marker, and it picks up the temperature changes as people walk by. Very useful. You can have them out there. They collect data, monthly, even yearly, as long as the battery still works. And then you can go back and download all the counts. So they're very easy to install and use, and the downside is it doesn't pick up everything, right? So this is just picking up the number, the volume. So you have to actually go out into the field and collect all the other information that it's not reading, things like mode split, directional split, so where are they actually going. There is error associated with using the trail counters. Obviously, if you've got 2 people walking side by side, or if you have like the entire cross-country team running at the same time, the trail counter doesn't know how to deal with that. So it's really important that you're out there in the field getting some of that raw data and comparing it to your automatic counts and adjusting for those volumes and those errors. So we did a combination of that. So we had the automatic counters out there, and we had students and myself out in the field getting a lot of this information and figuring out what's actually going on. And then the last part of the data collection was using a survey. So trying to actually get really detailed information from the users about how and why and what they're doing on the trail as a way to kind of motivate and figure out, how we're going to do additional extensions on the trail, or, areas where we need to maybe do more operations and maintenance to improve and pave those areas. We asked a series of questions. Some of them were very, very detailed about, how much money are you spending when you travel on the trail? There's a lot of destinations along the trail. Where are you going? How often are you going? What mode are you going? How many travelers or dependents are you going with? And this is really where we got a lot of our detailed information. So it was a really great opportunity to talk with the users one-on-one, and it provided insights that spurred some kind of improvements year after year on the trail coming from the users directly. So based on those 3 data collection methods, we were able to get some demand results. So ultimately, we're able to look at things like hourly averages and pick up where are those peaks within the day. We noticed peaks around lunchtime and again in the afternoon, so that kind of makes sense when people are out and about, getting outside of work, maybe going for lunch or going for dinner, they're using the trail. As well as day of the week, so we're able to see when are people using it on average, and based on our data, we have this peak in the middle of the week and then again at the end of the week, but this actually makes a lot of sense for the area that we're in because Lewisburg hosts a multiple county farmers market on Wednesdays. And we've noticed that this is how people are getting to the farmers market now. They're not driving anymore. They're using the trail to get to the farmers market, which is really, really is beneficial for the farmers market, but also it shows that you can start to make those changes with getting people to get outside their car. So that really makes a lot of sense. And ultimately, the goal was then to get a yearly travel volume. That was really our end goal. And we were able to do that. The first year, we didn't have a full year's worth of automatic counts to help get that yearly travel. So what we had to do is we had to take the months of data that we had and fill it in with using the National Bike and Pedestrian Documentation Project's seasonal adjustment factors. So if you know your volume on certain months, based on your climate, it allows you to have these percentages to adjust for months that you don't have data for. And so based on the climate we're in the long winter, short summer climate, although I'd have to say within the last 2 years in Lewisburg, they need something called the really, really, really long winter, short summer, because we had, many, many days with below zero and significant snowfall that really prevented pretty much even your avid users from using the trail. So we saw a drastic decline within the last 2 years of traffic on the trail due to those winter months, which were not picked up by the seasonal adjustment factors. But this is a way to, figure out your yearly travel, and we were able to do that for the last 4 years that we've had the trail, and we continue to do so as we build more and more stretches of trail. I'll show you a little bit about the extension, but this is a really valuable piece of information. It helps us to figure out what's changing year after year, how are destinations along the trail affecting, and ultimately looking at this business connection. So if we know more people are using the trail, how's it affecting the land use around it? So we've noticed that a number of destination points have built connections to the trail to get users to use the trail and then access their facility, whether it's we have a natural food store, the farmer's market, even the gas station. There's so many places that have actually put, for the mini mart, people to go get snacks and stuff and then go back on the trail. So we've seen those connections happen. We've also looked at businesses that have relocated. So they used to be in the downtown of Lewisburg, not on the trail, and they've actually moved their business to be on the trail itself. Things like Earl's Bike Shop, it makes sense for him to be on the trail. He has bike rentals. So people want to have a really easy access to that facility. And so this is changing the economics in the Lewisburg area. And ultimately, we've seen a significant demand for expanding the trail into new sections. So right now, the trail actually ends on one side of a major route, a U.S. route corridor. So it's Route 15. I don't know if anyone's from that area, but it bisects the area of Lewisburg. So the trail ends on one side, and the downtown Lewisburg and Bucknell is on the other side of the road. And so right now, some people are driving parking their car, and then getting on the trail. So our goal is to get the trail into the downtown. And we've noticed that, to get into the downtown, we're going to have more economic development, more people are going to be using the restaurants and things in that area. And we've, through the survey, have asked, how much are you willing to pay for something like this? And we've seen significant support. And right now we have a section that is under construction right as we speak. It's supposed to be done this week, the first section of the trail in the downtown area. So it's pretty exciting. The last thing I wanted to talk about here, this is the second project, and I'm just going to brief on it in terms of the idea of if you're building more trail, which we're doing in Lewisburg, how do you ensure that that development process is sustainable? So this is, right now, since we're building new sections, we want to think about the sustainable practices that we're using in the planning, the design, and the construction phase. We know that once the thing's built, it promotes sustainability, but how are we going to get there, and how can we make sure that the process is sustainable as well? So the goal is to look at a lot of sustainability metrics that already exist. So those of you that are familiar with rating systems and things like LEED, right? LEED does green building. You can measure the relationship of how sustainable one building is to another based on its certification level. LEED for neighborhood development does that for neighborhoods and communities. INVEST is one that looks at sustainable highways. Envision actually looks at multiple types of infrastructure. And then some of these other ones here at the top actually are all different types of roadways. So they're rating systems to measure the design and the construction processes of the roadway itself. Our question was, how are we going to use this for something like a shared use path, which is somewhat similar but different. It has different goals and different motivations. So we needed a rating system specific to developing pathways for ped bike usage. So that was our goal for this project here. We used a very kind of comprehensive process. So this actually builds on a project that I worked on with Professor Sue McNeil, actually when I was at Delaware, where we looked at developing rating systems and how you can actually do it in a thorough manner. At the time, there were rating systems that actually didn't disclose how they were developed, so you didn't really know why certain metrics received some points and why other ones didn't. And so we kind of went through this process of saying, okay, you have to go through and identify your credits. You have to go through and figure out how much they're important to your overall goal. So if there's an importance level, and how are you going to match those points to that importance level, you can do that through using something called HP. Analytic hierarchy process. It helps you to compare qualitative concepts to each other and ultimately rank them based on their importance to an overall goal. So if you know that credit A is more important than B and B is more than C and so forth, you can assign points based on that process. And so we use this method towards this new project of looking at for shared use paths and ultimately developed a rating system that has a series of credits, and obviously I'm only showing very few of them, but there's over 30-some credits in the rating system with the process of going through, and we surveyed a bunch of experts and said, okay, can you tell us which ones are more or less important to each other? We did the AHP weighting process. We assigned points. We developed a rating scale, and ultimately this reflects something similar to like LEED for green buildings, except it's green paths and it's for trails or shared use pathways. And we were able to apply that to the Buffalo Valley Rail Trail. So we did a case study, and we were able to actually go in and see how many points were earned for each of the different categories. Just like you would do any other rating system, you could say, okay, well, I could improve on this area, or I'm doing really well in this other area. For our purposes on the Buffalo Valley Rail Trail, we found that there were opportunities to improve in the continuing practices, which is something that the county has actually taken the information from this and changed some of their operations and maintenance strategies based on the credits. And with this new extension that's going in, they've now thought of new ways to address the design and the construction practices that they didn't do in the existing. So this rating system has motivated them to make some changes in their processes, in their construction. So when we do the extension, when we applied this to the extension, we actually saw that there was more points earned because they have the motivation to include more of the credits into their process. So I just wanted to kind of wrap up and say, you know, there's a lot that we can continue doing with this area of pedestrian and bicycle infrastructure and trying to motivate people to use it not just for recreation but for commuting as well. I think, you know, there is a certain location where these things work, and there's an opportunity to get people out of their cars, and we should continue to do that. And also thinking about how we develop those things. So yes, we know that they promote sustainable mobility, but when you go in and you design and you pave a whole railroad right away, how do you make sure you're doing it with sustainable practices? So you can use metrics and rating systems for that. Other research needs that I think can be touched on, you know, I mentioned a little bit about smart growth. I think this area is really kind of taking off, and there's a lot of tools and there's a lot of guidance out there in terms of how to actually implement smart growth into communities. But I think that there's a lot of challenges with taking some traditional tools and applying them in different areas. So Bucknell University, Lewisburg, Pennsylvania, we're very rural, right? So a lot of these tools and a lot of these guidance manuals are a little bit challenging to think about, okay, well, what does smart growth really mean to us, right? Rural versus urban, very, very different. So how do you kind of morph those into what you need? Connecting it to public health and wellness, I think this is a major thing that we could be looking at. So how do these land use changes affect our growth and our society, healthcare and population growth and things like that? I also put technology and pedestrian bike data. I think there's a lot of new stuff coming out in addition to those infrared trail counters. There's data and there's technology out there for more rigorous data collection methods. And especially as our trails get bigger and connect multiple jurisdictions to each other, you know, not just multiple jurisdictions, but multi-state, you're going to have high levels of data collection for pedestrian and bike. And right now we're really focusing a lot of our data collection on cars, which is good because that's what we need to be doing, but I think we also need to be kind of balancing that out a bit and allowing agencies from multi-states or multi-jurisdictions to be able to talk in the same language to each other and promote these types of resources. And then lastly, thinking about those economic impacts and those socioeconomic benefits. I think trails and shared use pathways do a lot to get people outside their car and getting people to use some of the kind of the community connectedness and social interaction that we need kind of at this point in the 21st century, you know, getting people out of their car. So that was mostly what I wanted to say. So I guess I will open up for questions. I will say that the two projects that I just mentioned are in publication, so if you want more information, that's kind of the papers that support those projects. So thank you so much.
Okay, we have some time for questions, so questions for Michelle, please.
Wondering how that trail's going to get across the Route 15.
Good question. So I actually had a senior design team last year do a feasibility study and a design of it. And essentially, going over is always challenging. Going under is also equally as challenging. Cost is a concern, as well as ADA accessibility due to kind of slope requirements. We're not going to be able to build a bridge. We can't do an underpass. So it looks like at this point it's going to be at grade, where you would have a pedestrian signal. So you'd have to dismount your bike and then push the button, wait for that timing to change, go to a mid-block, kind of crosswalk, push another button, and then cross again. So right now this is under evaluation. Currently I think it's in the hands of PennDOT right now, and that's considered phase 3 of the extension. So phase 1 is already built, phase 2 is under construction in the downtown, and then phase 3 is figuring out how do we get these things to connect. So, but right now we have a pedestrian signal down at the crossing of 15 and 45, which are the two major U.S. routes. So right now people are kind of diverting and crossing there now temporarily until we can get that actual crossing at the alignment that we need. It's a good question though. Yeah. Thanks.
Safety and security of these facilities are the project.
Yes, absolutely. So we actually included that a number of questions about that in the survey. There was a lot of concern actually up front prior to the development of the existing trail about how would something like this affect the adjacent abutters. So a lot of land use owners were avidly against putting in the trail because they were concerned with safety, security, crime, all those types of things. But what we've actually seen is it actually has not been a problem at all. It's actually been less of a problem than people had anticipated. The land use owners that were concerned about safety actually now are supporters of the trail, as they are now using it as their primary way of getting around. And for them, it's a straight access point, right? So for them, it's been a great asset. They've been the ones promoting the extension, which is kind of interesting to see. And especially with the rating system we developed, we have a whole section of metrics focused on safety and security, and we found that a couple of surveillance equipment, things like that, really can do a lot. But essentially, getting people, it's kind of like eyes on the road. The more people you have out, the more safer it is. So it's been nice to see that. It's a good question. Yeah.
What about the other safety? I'm sorry, the question behind. The safety of the actual travelers in the trail. As the trails get used more often, the volumes increase. Now you've got so much differences in speed oftentimes. I know with vehicular traffic, that's what causes so many crashes. The speed differential. Have you seen anything research in that area or evidence of safety concerns from that perspective?
Yeah, at this point we haven't had, I wouldn't say, unless we have a major, when we have our events, our 5Ks and major cross-country events on the trail, then we see some severe volumes and some differences between that. But it's been a kind of, it's used at it's still used at your own risk. We have rules and we have regulations, but most of the people are very respectful. There's a lot of, I'd say, opportunity. When you do have to slow down, people have learned the rules. It takes a little bit of behavior to get used to in terms of knowing, okay, you ride on the right, pass on the left type of a thing. It's the same as when you drive, and until you get those kind of rules and regulations in the mindset, then the community has adopted it, and ultimately everybody is following that by the time, now we're in our 4th year, and I think now people know the rules of the trail for the most part. But that's a good question, yeah. Go ahead.
Do you know property values change all that?
So this is an interesting point because we actually want to do a study on that specific to this area, but based on other trails and research that we've done, they have found that trails have actually increased land use. There's a land use value associated with having a recreational facility accessible to those areas, not only from a commercial standpoint, but residential as well. That has been a selling point for many of the residential areas in our community. I was actually, when I was buying my house like a year or two ago, that was the point that everyone had at the top of the line, near the rail trail, exclamation point, right? Because that's what people want to be around. People want to have access to that amenity. So yeah, it's been great.
In the survey that you conducted, did you get a sense of whether or not this is, people are using the trail as part of the shift, or is the trail in itself a destination? So people are actually shifting their destination choice to something along the trail. Do you have any sense of that?
I would say it's both. I would definitely say it's both because there are certain, until all of your destination and needs are kind of within that reach, it's really hard to say, but I would say a lot of people were clearly, through the survey, saying that they are now making the conscious decision that if they need to go into the downtown, for example, even if it's something not accessible to the trail, they're now thinking about using the trail as their right-of-way, as their corridor to get there. And that's really, really huge. And then obviously, as the demand has been happening, more businesses have been wanting to be adjacent to the trail. That's been now emphasizing the need for a destination that's closer, that we didn't foresee that. We didn't know that businesses were going to go up and move from, downtown Lewisburg, which is a very popular place. So for them to do that, they have the demand, they want that demand, and now people don't have to, go as far to begin with. So it's kind of a two-pronged approach, I'd say, but yeah, cool. Yeah.
On breaking the cycle that we started with in terms of
Yeah.
transportation. So you also talked about the differences between rural and urban areas. So how do you extend this concept of rural, transportation or train system into urban areas? Because, you cannot live local. You have to live far away places and then commute. How do you adjust this model for developed places like that?
Well, I guess I would say I don't think you always have to live farther away. So how do we get people to, first of all, want to live closer to where their work is? I think the first question, right? So if we can get people to feel more comfortable with living closer to where they work, then these types of models are more effective, obviously. But I think, you know, the rural applications of this versus your urban, looking at your, not just the trail segments, but looking at the trail interconnectivity. So longer distance traveling, obviously, you know, with biking, you have kind of a limit on that in terms of how far you can go. And you would say, you know, okay, what is that bikeable shed? What is that walking shed? What's that bikeable shed? And let's work within that. Let's work within that for now. But ultimately, you know, we're starting to take a step back and say, okay, we want these trail segments to interconnect. We want to look at longer distance travel through things like cycling. So how can we do that? And the only way we can do that is through agencies collaborating on these types of segments, which is kind of newer of a concept. We know with roads, you know, agencies are talking to each other about that. But do we have agencies doing the same with trails? And that's still kind of an emerging concept, I would say. But I mean, obviously, you know, certain types of facilities are going to work in some areas and some are not, but I think the concept of getting people out of the car, whether it's just to use that trail to get to a transit hub, right? If it's a longer commute that they have to do, making sure that they're getting there maybe not by driving, maybe by biking or walking. So, yeah. Thanks.
Okay, thank you very much. Okay, just if you all would, one more time, let's thank our panelists. This is not an easy task to have. Okay,
We wanted to thank the panelists for all their time and effort. Just a little thank you.
Yeah, so as Alan's distributing those, so all of the presentations are available online. So the easiest way to get there is nationalutc.org, and then in the right column is the top news post related to the emerging research session. So definitely, I think they have lots of great stuff to share. You want to go to your hotel room, read those equations, and then come back. Got some options.
That's what I'm going to do.
So, but those are there. So, thank you.
Just a little bit of housekeeping. We want to be sustainable, so take your water with you. Fill it up in a fountain that's right around the corner. The buses are here for the trip to UD. We're going to be going to campus to have 2 demonstrations. We have a handout that we're going to pass out to you if you load on the buses. Delaware Express buses are right out the front door. So, thank you.
Don't know. I was kind of, did people have time to drop the